Okay, so hi everyone. So today we will talk about similarities and anomalies detection in network mapping. So I'm Camille Mouget and this is Xavier. We are coming from CEA, not CIA, and that's why you had red everywhere. This work has been done during the internship of Xavier, so I'm the mentor, he's the trainee, obviously. Uh, okay. You have to know that Xavier was a teacher, but he's no back a student, so he was on the dark side and he's no back a Padawan. Okay, so today we'll talk about network mapping. So I think that you already know this, but it's kind of the same thing that satellite imagery. It's partially comparable. We have two kind of approaches. So the first one is the passive one. So we just look at the network and try to guess what is happening. And the second one, the active, the one we will use, we send probes and watch the results of these probes and base our result on it. Why we do this? For the blue team, for Defender, this is for research studies, and this is to know. It is a way to know our network as an attackant can see it, and it's also a way to, as Biondi said, a way to see our user click on everything on the internet. So a big red button with the download, you know. And for the red team, the goal is obviously to retrieve information on a given target or observe this target over the time and maybe find potential vulnerabilities or at least low-hanging fruits. So yes, keep calm. Yes, we can. What is the idea? We want to analyze the targets, so we send our probes. There is some biases. For instance, if there is a firewall or our scanner has biases, we use Nmap or Mascan or ZMap, and there are drawbacks due to these tools. And our IP can be detected or blacklist, or so there is some biases that we have to know before doing our scan. Nowadays, there is a big rise of massive scans, so we can actually do a scan over a country or over an autonomous system or maybe over the whole internet. That's been done, and this is very feasible. So you get a big number of results, but we don't have many people to analyze it, contrary to other countries, at least one. But we have many cores, so we'll use the machine to do it. So what tool? So to our knowledge, but so just the public available. There is scans.io. It's a good one, a big source of data, but we want to use our own data. So you may know Shodan, which have a good API, really a beautiful interface, but we don't want our results in the cloud. You get Zoom High, the Chinese version, because as porn there is always a Chinese version. You have the Quartz Lab Ivy, but it's private. And thanks to Snowden, there is a GCIQ agenda, which was top secret. So the one we'll use is IVRE, which stands for Instrument de Veille Réseau Extérieur, of course. And in English, Digital Recognition of Unknown Network, so obviously drunk. It is open source, it's developed by a colleague, which is Pierre. And that's the one we'll use. On which data? We talk earlier about Modbus. So we'll focus on a scan which has been done on the whole internet on T-Sport, which is the default one for Modbus, and you can get the result on the internet at this link. So we use an open source tool, and the sample is already available. So all of our results are reproducible. So I just want to introduce a manually digging and show you what we can obtain without the work we've done. So this is the web interface of Ivre. There is a workshop on Ivre, so I don't spend many time on it. So we'll first maybe look at the address space. Remember that this is a scan that has been done on the whole internet, but you can see that the address space is not uniformly reparted over the available addresses. If we look at the geographic repartition, you can see that it's mainly in the US and Europe. And yes, we can have a zoom on Europe, but just for fun. So maybe at Grenoble. So if you look to the top autonomous system, maybe not just in Europe. Okay, so we will not look at the top autonomous system. Maybe to the country, because Orange. So the top country, it is okay. So the first one is the United States. That's quite common, but actually the Turkey is not the common second top values. For instance, if we take a random scan on the internet, that's what we got. Okay, so usually you have the United States, then the China, then the Korea, and the Modbus scan, the Turkey is as we can see, an anomaly. So if we just focus on it, we may look, for instance, for uncommon service. And maybe because we talk about PLC, the soft PLC maybe? Yes. And here we go, we have this one, which is the only one from our scan, which is the only one exposing this service on the internet with the Modbus 2. So maybe an interesting target. I think it's online. Still online. Okay, so this is just manually digging, and we can find some interesting things, but it just rely on our knowledge and our experience, and this is a human bias, and we don't want to have a human bias. And additionally, looking for this kind of targets is very time consuming. This is just one, but the whole Modbus scan is about 10,000 maybe, 10,000 hosts maybe, so it can be very time consuming. So what is our wish list? We want to have a way to automatic grouping of similar hosts. That is to say, I don't want to consume time on a printer than on other one printers, because this is exactly the same. If I found a vulnerability on it, I want to have all of them, and if I don't find something interesting, I don't want to spend time on other ones. I want to have a way to unfile uncommon hosts, and maybe machine learning with the clustering and anomaly detection can be the solution. So this is what Xavier will talk about.
Okay, so I'll present briefly the machine learning. To say, when I started the internship, I thought that machine learning was more about the picture on the left, and actually it's more about the picture on the right. So I was a bit disappointed. What is machine learning? It's a field derived from pattern recognition and artificial intelligence. This is closely related to computational statistics, as you saw on the picture before. But hopefully for us, all the hard work has already been done by smart guys and mathematicians. The machine learning can be divided in two main categories, which are the supervised machine learning algorithm. For instance, if you have an algorithm which will try to recognize a picture that you give to him. In the first step, you have to give him, for instance, a picture of a cow. You say, this is a cow, that is a cow. And then you give him a picture of a beer. You say, this is a beer, remember it. And in the second stage, you give him a new picture and you hope that the algorithm will be able to find this looks like a cow or this looks like a beer. This is great, but in order to do that, you have to previously label a set of data. And in the case of scanning the internet, if you scan, for instance, 10,000 hosts, you don't have time to label manually each host you had. So this is the first drawback. The second drawback is by doing that, if you take the time to label all the hosts, you would say, okay, for instance, this machine should be considered as a web server. This machine should be considered as a printer. And if you do that, you will introduce a bias, which is the human decision you made earlier. So we will focus more about the unsupervised machine learning algorithm, which are kind of the same thing, but you don't have to label first. So this is cool. The algorithm will try to find pattern in the data by himself, and by doing that, sometimes it even find patterns that the human eye would not have seen by himself, which is pretty cool. So just to remember, we would like to be able to do three things. The first thing is grouping hosts by similarities. This is done by clustering algorithm, because if you have 1,000 hosts with an Apache server on it, you don't want to spend time analyzing each one of these 1,000 hosts. So grouping is important for that. Second thing we would like to do is emphasizing uncommon hosts. That is to say, anomaly detection, or sometimes you can find strange things and fun things in that. And the third thing you would like to do is being able to plot or to represent your data. And in our case, when we do a scan, for example, with Nmap, it will scan about 1,000 ports, the 1,000 most common port according to Nmap. And we will see later, but that gives us a vectorial space of 1,000 dimension, and you cannot plot 1,000 dimension, or at least you would not be able to picture it by yourself. So being able to put that in 2 or 3 dimension is way better to represent the data. So the problem is that we have the algorithm. They have already been done by smart guys. We have the scan result, but the algorithm wants matrices for input. So the question is how you could transfer the scan result. This is a Nmap scan result on the left to a matrix, and do that in a relevant way. So don't, do that so that the information you keep is relevant. So we had several approach for this. We can call that experimental approach. The first one was a binary solution. So you consider a host, like the host number 1. You list all the given port you scanned with Nmap. So for instance, 1,000 most common ports according to Nmap. And you just note if the port is closed or if the port is open. If the port is closed, you put a 0. If the port is open, you put a 1. That gives you a matrix. And with that matrix, you run the algorithm. This is great. It works. But while you are able to spot, for instance, web server for a part and SSH server for another part, the thing is you won't be able to discover a host who's running something crazy on the port TCP/22. For instance, if someone does that, so the host number 1 run OpenSSH on the port 22. Okay, that's really common. But the host number 2 ran Emap daemon on the port 22. And with that technique, the binary solution, you won't be able to spot that. And we would like to spot that, obviously. So the second approach we did was a frequency solution. It's basically considering all the hosts you've scanned and make the statistics on those. And you look for example for the same host, OpenSSH. Let's say that 70% of the time this is what responded on the port 22. But the EMAP daemon was really uncommon. So if you put the frequency instead of just 1 or 0, you have something like this, really different, which will allow the algorithm later to focus that the host number 2 is really uncommon beyond the other host. So the first algorithm we will speak about is the principal component analysis. It's about representing data in high dimension and getting them back in lower dimension. And by doing that, you want to lose as less information as possible, or variance. So here's an example. You have a two-dimensional data set. And as you can see, there is one dimension which is more relevant than the other. All the information is gathered on the big segment. And if you do the projection on that axis, you will lose about 5% of information, but you will divide the dimension by 2. So here's an example where it can be useful. This is a study about what people in Great Britain eat and drink. It's in gram per person per week. You see there is 17 food or beverage which are in the chart. So 17 dimension. You can see all the data are kind of different, but you cannot see a trend, or you cannot see it easily. But if you do the principal component analysis on those data, so 17 dimension, you've got this. So you will see that Northern Ireland seems pretty different from the Wales and England and Scotland. And if you do the same PCA on 2 dimension, you've got something like this. So Northern Ireland still is a bit different from the other one. And that can be explained, if you look back at the chart here, by the fact that Northern Ireland people eat way less fresh potatoes, way more fresh potatoes than the other, and way less fresh fruits or fish or alcoholic drinks. And for those of you who are as bad at geography than I am, it's fun because Northern Ireland is the only a country of United Kingdom which is not on Great Britain. Okay. So we will see how the principal component analysis is done on the Ivre Analyzer CLI tool. Okay, so we asked him to go to the category Modbus. We want only host with 0 to 10 port opened. And we plot that in 2 dimension. So we have 1,000 hosts that we selected. We plot that in 2 dimension. Okay, so here are our 1,000 hosts, and you can see on the chart here, the first graph on the top left is about what is important for the first dimension. So you see that the PCA decided that what is important for the first dimension, the x-axis, is the port TCP23, TCP22, and TCP21. Okay, so basically there is servers with, for instance, SSH server, telnet open or not, and that's what makes the difference in the x-axis. Same thing for the y-axis. And we can do that in 3 dimension, and if we do that in 3 dimension, maybe we will see that we gain some information. Okay, so in the 3rd dimension, if you can maybe move the graphic, there is a difference between two cluster of hosts, and according to the 3rd axis decomposition, you'll see that it's the port TCP 8080 which made the difference here. Okay, so we get back to our second algorithm, which is clustering. Clustering is grouping elements by similarities. This can sound trivial in 2 or 3 dimension because your eye can do that, but if you consider a vector space in 1,000 dimension like the one we have, it's not trivial at all. So here's an example. I consider 64 dimension. So that is 1 dimension per pixel. So the image on the top, on the bottom right, is 64 dimension gathered together. Each dimension can take 256 possible values, which is the grayscale value of the pixel. So 64 dimension, one sample, you take several samples like this. Each sample obviously represents a number, and you give that to a clustering algorithm. We choose to give that to K-mean algorithm. You say to K-mean algorithm, okay, I have my data, please do 10 clusters. We just say 10 cluster, and then the algorithm compute, and at the end we ask what is a cluster, what is the center of a cluster, and this is what it responds. So you can obviously see that the number are, you can see the numbers. So in our algorithm, we use the K-mean algorithm, which is great because it scales well in high dimension, and we are in really high dimension. It's easily parallelizable. And we use the dbScan algorithm, which is closer to what the human eye would do because it works with density recognition of each area. We'll see a quick example of how this algorithm works. So the first one is K-mean. So for K-means, we have to say how many clusters we want. So for instance, if we say here 4 clusters, the algorithm will try to get to a state of where it does not move anymore. Okay. So you can see that in this sample set, this does not seem to be the best choice. But if we do the same for the dbScan algorithm, which is based on the density of the cluster, okay, so it takes a bit of time for the demonstration, but you will have one cluster for the circle, one cluster by eye, and one cluster for the mouse. So that's what we want. Okay, so we'll see how it works in our database. So let's, for instance, cluster those in three groups with K-means. Okay. If we plot that in 2 dimensions, we'll see 3 colors, 1 color per host. And as you can see, this is not what human eye would have done. But remember that the algorithm works in 1000 dimensions, and then this is projected in 2 dimensions. So obviously there is some stuff that does not work great, or at least that does not seem to work great. Because if we plot the same host in 3 dimensions, you see that the yellow color seems to be on the bottom. So the algorithm works in high dimension, and that's a good thing for us because human eye would not do that. Okay. So last thing we will speak about is the anomaly detection. So this is the third algorithm to spot the anomaly. You have to remember one thing, that the anomaly is not something which is far from mean. For instance, here the anomaly in the center is obviously something abnormal, but this is exactly the mean of all the data. So being able to detect anomalies, for instance, being able to detect an Apache server running amongst several handman crafted HTTP server, or the other way around. There is 2 main kind of algorithm for anomaly detection. The one who consider that the data are Gaussian reported, and this is an assumption we cannot make. And the other one that suppose this is not. So we choose to go for this algorithm, which is the one-class support vector machine. Okay, so we'll see that on Ivre. Okay, so we take exactly the same data, and we will select 10 anomalies. So we search them, we select them, and once we have selected them, we can either plot them or display the host. So in this way, we are able to further analyze these anomalies through the Ivre interface, Ivre web interface. So we'll not take too much time for digging into those because we will see that just at the end of the presentation. Okay, so I'll let.
Okay, so we'll just introduce you some results as I think we don't have many time. So just how we can, for instance, targeting an autonomous system. Okay. So we will focus on another scan, which is a full scan of the Luxembourg, because there is a very interesting target in Luxembourg, of course. No, Luxembourg, as Luxembourg. Okay. What we can do now is maybe so look at the map. So we clearly okay. So I think there's just one city. We'll go to our tools. So the category. We'll just look for autonomous system first. Sorry. What are the autonomous systems in Luxembourg? This is this one, and we may look to, for instance, the Foundation Ristina. Okay. So let's focus on it. So this is the okay. So please use this as a filter in the tool, and we'll try to find what this AS looks like. Okay. Okay. So please plot in 2D. Yes. Okay. Use as you may see, this is how the data looks like, and this is because there is one host which is just alone, and that has been which is very uncommon, and this is because it is what we call the trivial honeypot, which is actually a server which answer yes on every port based on a random base. So if you just, for instance, cluster in two, so okay, okay, thank you. We'll work on demo. Okay, so please use two cluster comings and yes, so count, and we can see that there have been split in two, and there is just one host which is alone, and the other ones. So now we'll yes select yes. Okay, so and display this host, and if we go in the web interface, what we can see, so ID, okay, and this is a host with a lot of open ports and very uncommon ports like 1 or 3, which is not very usual. Okay, so we may now go to the second cluster, and we'll look like we'll okay. So we'll apply this time the dbScan algorithm to cluster this host, and it's quite longer. It's a bit more longer than the Camins one, and okay, it's very okay. So and what we got, it's a lot of cluster, and if, for instance, what are you doing? For instance, if we focus on the cluster, the one with the 7 hosts, and this host has been grouped, and this is the group that we obtained. And if you look at one group, what we got is okay. C'est pas grave, c'est pas grave, c'est pas grave. Putain. Roule. Okay. What we can see here is that all the hosts has the HTTP port open and the AT80 port open too. So this host has been clustered together because they are similar. Okay. If we look now quickly, because I think we don't have many time, to anomalies, with dbScan. Or just select anomalies. Just say yes, search anomalies and maybe 10. What this guy is doing to my computer. Okay, so this is the 10 most anomalies in this scan. And if you look to them, if we may look to them, what we got here is several uncommon hosts with, I don't know, this is, so actually this is not determinist because the algorithm use a random initialization, so that we cannot see, we cannot know in advance what can happen. But for instance, this one seems to have an FTP okay, and it has a APH server on an uncommon port, etc. So just to finish the talk, we cannot show you results in enterprise because it is quite personal. But you have in the Act more details on it. If you want enterprise results, do not hesitate to contact us. Okay, so just to conclude, this approach, we consider that this approach has to be used with the human manually digging, and this is just a tool, not the only approach to use. You have to go back and forth between the machine learning, the clustering, and the expert experience. The results are promising. We will continue to work on it, and the main difficulties is to represent, as Xavier said, as a vector or a host, and this completely determines our results. So we continue to work on it. So if you have any question, thanks for your attention.
I think we have time for 1 or 2 questions.
Sorry for demo.
So, hi. Did you use only Nmap top 1000 ports to generate your data?
This depends on what we want to obtain, of course. And at the Modbus scan, I think this is not our scan. They're coming from the blog of Pierre. And I think it's used here. You may use just a few more ports, but not every of them, because it is very long and time-consuming to run this kind of scan. But you can run a pre-scan thanks to ZMap or mass scans, and then scan with Nmap on an interesting target.
Yeah, because if the goal is to find vulnerable machines on the internet, you need to consider that Nmap is biased because the top 1000 ports, for example, don't contain port 2433, which is MS SQL, which is really vulnerable.
Yes, I think they are in it now.
Nope.
No, okay. And additionally, because this is the most ports used in Nmap, and Nmap is the most tool used, we can consider that someone is already in the place.
Thank you. Any more questions? Here we go.
Hi. It looks like there is still a manual intervention to see what is the cluster actually. And do you think it will be possible to, through machine learning, understand what represents the cluster?
Yeah, it might be possible, but if you want to do that, I think a good way to do that, to achieve that, would be to manually label the cluster first and say, okay, port 80 is most of the time for web servers. If it's linked to 443, it's most of the time HTTPS and HTTP server. But if you do that, you won't be able to spot anomaly easily like we did before.
Okay, thanks.
Thank you very much. Please give a hand to Xavier and Camille for that very interesting talk.